So today we are going to discuss what we have left in the last class regarding the equations, mathematical expressions regarding modulation, that is amplitude modulation, and what are the parameters through which we can understand the modulation schemes depend upon the critical modulation, over modulation with the help of modulation index. As well as we will go through the modulation spectrums through which each and every point will be clear with respect to the mathematical relation. That we can do with the help of frequency transmission. In the last class, we have discussed about the time domain characteristics for modulating signal and modulated signal, as well as carrier component. So one by one we will see, that is amplitude modulation. Okay. In this we are going to discuss about the mathematical relations, each and every point with respect to the equations. Now last class we have seen that this is the summation in which carrier amplitude, modulating signal combined with provided in the mixer in which carrier component frequency, that is cos omega ct, is available, and then we are getting s suffix am of t. This is the modulated signal. Once again I am saying this is modulating signal. Okay, and most important thing, this is the carrier signal. Okay. Now in this amplitude modulation, in this scheme we are going to change the characteristics of carrier component with respect to the modulating signal. Now with the help of this, the mathematical expression what we have written in the last class, again I am deriving it and representing for the understanding purpose. First we have considered m of t, okay, that is Vm cos omega mt. Vm is the amplitude of modulating signal, and cos omega mt indicates that it is a cosine signal with angular frequency omega m, where omega m is equals to 2 pi f. Then similarly, what is our carrier component? Carrier component also we have seen. Let us consider AC cos omega ct, where AC is the amplitude present in the carrier whose angular frequency is omega c, that is equal to 2 pi ft. Now it is not mandatory that both the signal to be cosine signal. The signal can be of sine signal, can be of cosine signal. For understanding purpose, I have just moved the signal as a cosine. You can consider modulating signal is a sinusoidal signal, and your carrier component is a cosine signal. Okay, any one of the component you can consider. Then s suffix an of t, modulated signal. This signal also we have represented in the last class. So according to this figure, what we have written, that first m of t is added to the amplitude of the modulating or amplitude of the carrier component. This is the carrier component. That means the carrier frequency and phase remain constant, but amplitude is going to change with respect to whom? With respect to modulating signal. So here I will write AC plus m of t into cos omega ct. So this is my modulated signal, as well as this whole thing I have written as envelope E of t cos omega ct. Now this E of t is called as envelope component present in modulated signal. Now what is the purpose of this envelope? This envelope consists of our modulating signal. So while demodulation, with the help of this envelope I can extract my modulating signal. And as I have told in the previous class, that the total carrier does not convey any sort of information, but it will carry your information. Your information is the modulating signal. Okay, that modulating signal will have the information, and carrier is only a unit or only a physical quantity which is going to carry that information and deliver at a destination end. So with the help of this envelope, you can understand that this envelope consists of two components. One, amplitude of a carrier, and second, amplitude of the modulating signal. So depend upon these two factors, we are going to see how this AM signal is generated. Okay. So at this point, you can see AM signal is generated. AM signal itself indicates what? Here the variation of the amplitude of a carrier is done with respect to the instantaneous variation of the amplitude of modulating signal. Okay. So for that I have written this. Now if I am going to elaborate this one, this equation, these all equations are trigonometric equations. Okay. So mathematically we have represented AM signal with the help of this S suffix am of t, which is equals to a suffix c plus m of t into cos omega ct. Now if I will elaborate this, now S suffix am of t is equals to a suffix c cos omega ct plus m of t into cos omega ct. Okay, so this is the equation what we are generating from the AM signal. Now in this equation it indicates that presence of carrier. This is the presence of carrier, because AC cos omega ct we have considered this is a carrier component. Then another one, that envelope what I have discussed, that AC plus m of t, I will elaborate. This carrier is also there as well as modulating signal is there. But m of t is a modulating signal which is imposed on a carrier. So cos omega ct. So here we are going to impose on cos omega ct, which is a carrier component. So that means in modulated signal, two informations are available. One is carrier information and one is our information. Carrier does not convey any sort of information, but our information is a modulating signal. So here the carrier is available. Modulating signal is imposed on a carrier signal. So this is called, notification is called as sideband. How this sideband will identify, we will see. So that means in AM signal we have three different components. One, as in the PPT what I have shown, that first component is a carrier, second component is the upper sideband, and the third component is the lower sideband. How to identify this sideband? Let's see. So here, if I will expand this, it is AC cos omega ct. M of t I can write Vm cos omega mt, because we have considered m of t as Vm cos omega mt, which is multiplied with cos omega ct. Now in this you can see that these both are in terms of cos A cos B form. So cos A cos B form means we can write as half of cos of A plus B plus cos of A minus B. Because if it is in sine term, we can write cos of A plus B minus cos of A minus B. That is the trigonometric equations we have a relation, I will write for you. If it is cos A cos B, which is equals to half of cos of A plus B plus cos of A minus B. Okay. Now here A and B represent the frequency. A is the higher frequency and B is the lower frequency. Now in this case, which one is higher, which one is lower? The lower frequency is our modulating signal and the higher frequency is the carrier signal. Now for this I can write A cos omega ct plus Vm by 2. So this is Vm by 2. And one more important thing. So it is Vm of 2. Done. So this Vm by 2, and here I will write cos of omega c minus omega m of t plus Vm by 2 cos of omega c plus omega m of t. Now here this represent, it indicates that the representation is done with respect to carrier component with two sidebands are available. Two sidebands are available in that I will show while representing in frequency domain. Omega c minus omega m is the LSB. This is the LSB component. Okay. And omega c plus omega m is called as USB component. That is called upper sideband component. Okay, while representing in frequency domain, I will tell how to represent all this. For the time being, for mathematical analysis, first component is our carrier, second component is our Vm by 2 cos omega ct minus omega m of t, and Vm by 2 cos omega ct. Like this we can write. Okay. Now one more important thing, if you are taking this AC outside, that indicates our modulation index. For the time being, I have not discussed about the modulation index. I have just expanded the carrier component with our modulating signal imposed on a carrier component. This is called as our sideband. This is called as our carrier. Now in AM, there are two sidebands and one carrier component is available. So this is my carrier frequency component or carrier signal is available. This is called as my two sideband whose amplitude is Vm by 2. Okay. Now this particular relation itself indicates that if I want to represent this, that means your center frequency is Fc. Let us consider like this. For this particular representation, if I am representing Sam, I will derive all these things. Sam of F in frequency domain. So center frequency is F. Then the amplitude of this is A. So amplitude is A. Now for omega c plus omega m means it is Fc plus Fm. So it is Fc plus Fm. Similarly, the lower sideband which is available, it is called Fc minus Fm. So these are the two sideband with one carrier component, and this is called as double sideband with carrier, BSB plus C. Your AM signal is also called as double sideband plus carrier component. So it is called as a double sideband with carrier. So here I am representing the frequency spectrum. Always remember this, spectrum means it is a band of frequency. Representation of time domain signal in a certain frequency domain, and it will represent in a certain bandwidth. Now this Fc plus Fm I can consider the higher frequency, and the Fc minus Fm I can consider lower frequency. So if I will ask what is the bandwidth of AM signal, that means higher frequency minus lower frequency. Simple. So in place of higher frequency I will substitute Fc plus Fm, and Fm is Fc minus Fm. So if I will solve this, I will get twice of Fm. So this is the bandwidth of AM signal. So for bandwidth of AM signal itself indicates that it is a twice of your modulating frequency. Now here what I have done, here I have considered only one modulating signal. So that means this is the derivation for single tone signal, single tone modulated signal. So here I will write it is a single tone modulated signal. So this is comes under single tone. Single tone means only one modulating signal is available. So this is the frequency spectrum for an AM signal. Now we will represent this all frequency spectrum one by one. How to represent this one? Why this particular position is chosen for upper segment? Why this particular position is chosen for lower segment? That also we need to incorporate. Okay. Now let's see. I will erase this. Okay. So is it visible? Okay. So up to this it is a general representation. General representation of a DSP with carrier, that is called as an AM signal. And that too it is a single tone. Single tone means it is only one single modulating frequency is available. If it is more than one number of modulating signals are available means it is a multi-tone signal. For that also we will represent. Okay. For the time being we will see how it will how we are going to represent in frequency domain. Okay. So that is called as frequency translation or frequency domain representation. Okay. Now first we need to represent the modulating signal. Okay. So for that I am drawing a modulating signal first. So this is my m of t and this is the time period and this is the modulating signal what we have considered in the previous class. Now this modulating signal, if I will take a Fourier transform, okay, if I will take a Fourier transform, the modulating signal will become x of f because m of t will become m of f because Fourier transform of m of t will become m of f. So this m of f is having a bandwidth of a spectrum that is plus fm to minus fm. So this is the first one. This is the first consideration. This is the first consideration of what? Modulating signal. So modulating signal frequency spectrum I have represented because this is a single tone means only one frequency is available and one frequency means it is minus fm to plus fm. Okay. Similarly, if I will consider the carrier, that also we have seen that carrier is having higher frequency as compared to the modulating signal. Okay, so this is my C of T and this is my T. Okay, so this is 0 and this is the amplitude AC and peak to peak is plus AC and minus AC. This is plus Vm and minus Vm. Okay. Now as we know that A cos omega Ct, it is a carrier component. Done. But when you transform this into a frequency domain, now what will happen? If you convert this one into Fourier transform, we will get some sort of relation like A by 2 del of f minus fc plus del of f plus fc. Del is called as impulse response, which is shifted from fc to fc plus fm, f minus fc and f plus fc. How we are going to identify this? With the help of Fourier transform, with the help of general representation of a Fourier transform. So Fourier transform will help to generate this cosine signal in terms of this impulse function, because this transformation already you people have known in your signal system. I may not discuss once again, just I am representing cosine signal with respect to this. Okay. Now this indicate what? if I am representing in four frequency spectrum, so this is the C of F. Okay, so there are two components are available. One is F minus Fc, one is F plus Fc. So that means there are two components are available at Fc and minus Fc. So that means here I can represent this is minus Fc and here I can represent it is plus Fc with an amplitude of AC. With an amplitude of how much? AC by 2. This is AC by 2. So this is the amplitude which is available in frequency component present in carrier represented in frequency spectrum. Now this frequency spectrum is a frequency domain, or you can say it is a frequency translation of your C of T. Now how these two spectrums are available, two positions are available, these two positions are available with the help of this equation. Now how I have got this one? You have to convert this form into Fourier transform. If you convert this cos omega ct into Fourier transform, you will get a by 2 del of f minus fc plus del of f plus fc. If it is a sine wave, here it will be a by 2j. That means imaginary component is available. Then now this is the carrier component and this is the message signal. Now next is our modulated signal. So that modulated signal we have seen, it looks like this. So here carrier is available. Carrier frequency and phase is not changing, but its amplitude is changed. That means if amplitude is changing and other parameters remain constant, that means I am getting amplitude modulated signal. Okay, so this is the amplitude modulated signal. Now how to represent this amplitude modulated signal in a frequency domain? It is a simple representation what I have done here. Okay, so here what I will do, the representation is, this is S suffix am of f, because we are converting the time domain function into frequency domain. So time domain function into frequency domain means the center frequency is our Fc, because presence of carrier is there. So due to the presence of carrier, the two frequency components are available at a plus Fc and minus Fc as per the above figure. This is the carrier. Okay. So according to this carrier, so here it represents that it is the frequency is available at a plus Fc and minus Fc. Now when this carrier is modulated with the modulating signal, what we get? The carrier is available plus modulating signal is imposed on a carrier component. So that means carrier is available and modulating signals are imposed on it. So these are the two modulating, upper segment and lower segment is available. So what is this? The carrier amplitude is AC by 2, which is present at plus Fc and minus Fc, and with the help of two segments. What is the two segments? If I will impose this one on this, that means it will spread to f plus Fc and f minus Fc. So this is Fc plus Fm, and this one is Fc minus Fm. Similarly, this component is minus Fc plus Fm and this component is minus Fc minus Fm. So this is the frequency translation or frequency spectrum of amplitude modulated signal for single tone, because here we have considered that our modulating signal is having only one frequency component. If it is having only one frequency component, that means we can consider the single tone representation. So this single tone representation derivation is this. So it indicates what? Presence of carrier and the two segments in which the modulating signal is imposed on a carrier component. So these are the two sidebands are going to achieve. So this derivation itself indicates that this is your lower sideband, this is your upper sideband in terms of angular frequency. You can represent in frequency component like this. So first, modulating signal it is in a continuous form, convert into a frequency domain, that is m of f, and whose frequency varies from -fm to +fm. But basically the bandwidth of modulating signal is fm. I will write all those things. Next, the carrier is a component which does not convey any sort of information, but it have a higher frequency with respect to modulating signal. If you take a Fourier transform of a carrier component, you will get two spectral quantity, one at +fc, one at -fc. Done. Then when modulating signal is obtained, this modulating signal is imposed on this carrier. That means this particular part will be imposed over here. So this is the exact representation. In some of the book it will be written in terms of triangle. In some of the book it will be written in semicircle. In some of the book it will be written in terms of this arrow. It is same representation, don't confuse it. Okay? There is no confusion between all this representation. All are same. Either you represent in semicircle wise, either you represent in triangular wise, either you can represent in this what I will say, in spectral quantity or in arrow form. Okay, only need to represent the amplitude and the frequency position. So this whole method is called as frequency translation or frequency domain representation. This is called frequency translation. Means representing a time domain quantity into a frequency domain representation into a certain bandwidth. Now here what we have learned, if I will say what is the bandwidth of modulating signal, one by one we will start. So that bandwidth plays a vital role. Okay. So with the help of that bandwidth, how we are going to identify each and every relations. Let's see. So first, the bandwidth, BW, or you can write bandwidth. So how many signals are there? Modulating signal and modulated signal. So modulating signal is m of t, whose frequency component is fm. So if it is fm, your bandwidth, what I have represented, here you have to consider from 0 to fm. So this is the bandwidth for your modulating signal. Imaginary part we are not considering. So bandwidth for modulating signal is fm. For any modulating signal, any audible signal, which is your baseband signal or which is your modulating signal, the bandwidth will be its own frequency. Okay, so this is the bandwidth of modulating signal. Modulating signal. Then next, if it is a modulated signal. Modulated signal. Now if it is AM or DSBSC rather than SSBSC, this DSBSC and AM will have same bandwidth. Same bandwidth means the upper sideband means higher frequency component minus lower frequency component. In this figure you can see the higher frequency component is Fc plus Fm, that is called upper sideband, and the lower frequency component is the lower sideband, that is Fc minus Fn. If you solve this, then you will get twice of Fm. So this is the bandwidth of single tone modulated signal. So this is a single tone modulated signal. So it is a bandwidth of single tone modulated signal. So it is a bandwidth of single tone modulated signal. Why? Because in this modulation we have used only one frequency component or one modulating signal. So this is the basic representation of modulating signal and modulated signal. Now we will see how to represent this AM signal in terms of modulation index, because that modulation index plays a vital role. It will decide in which sort of modulation we have done, or in which sort of modulation we have transmitted a particular signal, whether it is a over modulation, whether it is a under modulation, or whether it is a critical modulation. It depends upon that modulation index. So for that, I am erasing this. I will keep this equation as it is because we will require this. Okay. Now see, modulation index. We can represent the whole equation for single tone in terms of modulation index as well as for multi-tone in terms of modulation index. See, so modulation index for amplitude modulation, we can write M suffix A. In some of the book it will be written in K suffix A. It is same. It is also called as amplitude sensitivity of a particular modulator, or this modulation index is also called as depth of modulation or degree of modulation. All the terms are same. Okay. So modulation index itself indicates that magnitude of modulating signal divided by the magnitude of the carrier signal. Okay. Now this M of t or AC, this M of t magnitude, here I can write it is Vm of Vm divided by AC. Now here three things will arise: Ma greater than 1, Ma less than 1, and Ma is equals to 1. Now what it indicates? If Ma is greater than 1 means your modulating signal or this M of t amplitude is greater than carrier amplitude. In practical case, we are avoiding this sort of case, because if these sort of things have happened means over modulation will be done, then unnecessarily noise effect will be more, because at zero crossing there will be overlap of signals will be there, phase transition will be there, phase may not be same at that particular point. In AM, phase remain constant as well as frequency remain constant, and that is called as over modulation. Okay, that we will see. Similarly, if Ma is less than 1, we are preferring for this Ma less than 1. Here, what I have done, here whatever the modulation representation I have done, it is with respect to Ma less than 1. That is called under modulation, or it is called as proper modulation, in which amplitude of the modulating signal is less with respect to the amplitude of carrier signal. Okay, and if M of t magnitude is less than carrier signal. Similarly, Ma is equals to 1 means here the magnitude of modulating signal is same as carrier amplitude. If these two amplitudes are same, then I can say modulation index is 1. So this is called critical modulation. We will see all those figures later on. For the time being, just remember this. This is critical modulation, this is under modulation, and this is over modulation. Okay, so this is over modulation, this is under modulation, and this is critical modulation. So depend upon this Ma, the modulation schemes are going to be represented. So in this figure I can say that this modulation is done for Ma less than 1, for under modulation. Okay. So up to this it is clear. Now we will represent these equations for single tone modulated signal in terms of modulation index. So let us once again write S suffix am of t is equals to AC plus m of t whole into cos omega t. Done? Now take AC as common. So you will get m of t divided by AC whole into cos omega t. Okay. Now in place of m of t, substitute Vm cos omega mt divided by AC whole into cos omega ct. This I can write. Now what is this? This Vm into Vm divided by AC is nothing but modulation index. So here I can write AC whole into 1 plus MA cos omega mt whole into cos omega ct. Okay. So this is the AM equation for single tone modulated signal whose modulation index is MA, where MA is equals to Vm by AC. So this is the general representation of AM signal in terms of modulation index. Okay, this is the single tone representation. Now if it is multi-tone means more than one number of modulating frequencies present which is need to be modulated. So depend upon those things, again we have to come across bit by bit of this modulated signal. So up to this it is okay because we have represented the AM signal in terms of modulation index. Okay. Now this you can expand it. Your component is available as AC into MA, then the side length. So if you solve that AC into MA, again it will become as a VM. Okay. So that is the representation for single tone. Similarly, we can represent for multi-tone also. How? Let's see. And for multi-tone, your modulation index will be different because there are n number of modulating signals are available. So modulation index is going to be different for each and every one. And for that also we can represent the frequency translation or the spectrum which is available. For modulated signal. So step by step we will see how these multi-tone signals are going to be represented. So first single tone is over. Now we will go for multi-tone signal. So multi-tone signal means your modulating signal M of t may have more than one number of modulating signals. Now let us consider there are two modulating signals are combined and then it is modulated. So there are two different modulating frequencies are available. So if I will expand this one V1 cos omega m1 of t plus V2 cos omega m2 of t. So this is the two modulating signal. If it is more than one means it is called multi-tone. So here m1 and m2 two different frequency components are available. So for this we can consider it is FM1 and for this we can consider as FM2. And FM2 is greater than FM1. Let us consider this also. Because there are two different frequencies, they may not be same. So anyone is a smaller quantity with respect to other one. So let us consider this modulating signal is greater than, means this frequency component is greater than this frequency component. And your carrier frequency is very greater than with respect to F1 and F2. Now we will write the modulated signal. So S suffix AM of t, again we will write the equation AC plus M of t into cos omega c. So this is the general representation of AM signal. Now what you have to do, you have to substitute this value here. So it is AC plus M1 of t plus M2 of t whole into cos omega c. Then expand this. So we will get AC into cos omega ct plus M1 of t cos omega ct plus M2 of t cos omega ct. So it is more than one number of sideband signals are available. Two sideband for M1 and two sideband for M2. If it is a single tone, upper sideband and lower sideband correspond to the message component, but there are two symbols are available. So that means two message components are available. That means we have to identify the two other frequency component. Okay, for that we have to represent it. Now for this, when I am going to expand this relation, I will write S suffix AM of t. First component is carrier, which remains as it is. A carrier component is available. Done. Second, if I am going to expand this, what I will get? It is Vm1 divided by 2 cos of Fc minus Fm1 plus Vm1 by 2 cos of Fc plus Fm1 into T into T. So these are the two sideband which are extracting from M1 of T cos omega ct. Similarly, if I am expanding this M2 of T cos omega ct, I will get Vm by 2 cos of Fc minus Fm2 plus Vm2 divided by 2 cos of Fc plus Fm Fm2 of t. So that means when it is a multitone, that means more than one number of modulating signal is available. That means how many spectrums are available or how many frequency components are available? First, carrier, two sidebands for M1 of t and two sidebands for M2 of t. So for M1 of t, this is the LSB, and for M1 of t, this is the USB. Similarly, for FM2 means modulating signal second one, this is the lower sideband and this is the upper sideband. So that means how many components are available? The components are available is total 5 components are available. First, carrier, then second is two sideband corresponding to the message component M1. Third is the two component available for message component M2. Okay. Now this is your LSB, this is your USB, this is your LSB, this is your USB. Now how to represent this one in frequency transmission form? It is a very simple method. As this spectrum, what I have represented for the single tone, similarly I have to represent for multi-tone. Okay. And amplitude is also going to be represented for them. Now, so first I will represent in frequency domain for both this side. Both this side I will represent first the carrier component because carrier is available. So first, this is my carrier. This is my carrier. Okay, and this is my S suffix am of f. Okay, so this is my carrier. So AC cos omega ct, transform it, you will get AC by 2 and frequency components will be available. So this is my AC by 2 at plus FC. This is minus FC, AC by 2, because the frequency transformation we are doing. Now, from FC, the lower frequency first we have to identify, then with respect to the higher frequency. Lower frequency here we have considered FM1 is the lower frequency. So first I will represent the lower frequency component. So it is FC minus plus FM1. Similarly, lower side band is FC minus FM1. Then next, for the higher frequency component for the modulating signal second one, since FM2 is greater than FM1, that means it will lie here because it is greater. So it is FC plus FM2. Similarly, here I will represent FC minus FM2. So these are the spectral quantity, or these are the spectrums whose amplitude is Vm1 by 2. This is also Vm1 by 2. This is Vm2 divided by 2. This is Vm2 divided by 2. Same thing you can represent for the left hand side, because the frequency component we have chosen for plus Fc. Similarly, the reflection side also you can represent. There are two field spectrums here because there are two modulating signals are available for multiple. So here it is Vm2 divided by 2, Vm1 divided by 2. This is Vm1 divided by 2. This is Vm2 divided by 2. Here what happens? Here it will be minus Fc plus Fm2. It is minus Fc plus Fm1. Similarly, minus Fc minus Fm1. This is minus Fc minus Fm2. So these are the frequency components available both the side with respect to the carrier frequency. Here there are two modulating signals, means it is a multi-tone signal, and multi-tone signal is having, here we have considered two signals, that is called multi-tone. So two signals means there are four spectral components will be available each of the side of our carrier. So this is our carrier and there are two components are available. So there are four sidebands are available, two LSB and two upper sideband corresponding to the message signal M1 and M2. So this is the frequency translation represented for our multi-tone modulating signal. Okay. Now same signal you can represent in terms of modulation index. How and what will be the net modulation index for our multi-tone signal, that we will see. So here in multi-tone there are two different frequencies we have considered. You can consider more than one number of frequencies also, M1, M2, M3 or M4, depend upon the requirement. So here the same representation I am going to write for AM signal. Okay. Now let us consider this M of t consists of two modulating signals. Two different signals are combined, low frequency component. So it is AC plus M1 of t plus M2 of t whole into cos omega ct. Then now what we are going to do, take AC common, you will get m1 of t divided by AC plus m2 of t divided by AC whole into cos omega ct. Done? Now here what happens? Here I can write AC in place of m1 of t, we can write v1 cos omega 1t. So that v1 by AC is called as m1. Okay, m1 into cos omega suffix m1t plus m2. m2 is what? m2 is vn2 divided by AC into cos omega m2 whole into cos omega ct. Here I will multiply. Done? Now what is m1? m1 is vm1 by AC. What is m2? m2 is the modulation index of the second modulated signal. This is the first modulated signal. Here because there are two signals are available, two modulating signal. So m1 is the first modulation index, m2 is the second modulation index. But when I am going to modulate it, only one modulation index we are going to find out. How? See. So the net modulation index MA is equals to root over of m1 square plus m2 square. So whatever the modulation index we have got from these two relations, simply you have to take a square root and individual square component. So this MA is equals to root over of m1 square plus m2 square. Now here we have considered only two, but if there are more than two number of modulating signals are available, or in a particular modulating signal there are three different frequencies are available, or four different frequencies are available, that means the four modulation index will be there. So for example, this I can write in generally MA is equals to m1 square plus m2 square plus m3 square plus dot dot dot. So this is the general representation of net modulation index for multi-tone signal. Okay, so this is the net modulation index for multi-tone signal. So whatever the modulation index we are going to identify, individually we have to identify first, then the net modulation index we are going to identify with the help of relation, that is MA is equals to root over of m1 square plus m2 square plus m3 square dot 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 up to how many number of modulating frequencies are available. Okay. So these are the simple relations with respect to modulating signal if it is a single tone, with respect to multi-tone signal if it is more than one number of modulating signals are available or more than one number of frequency components are available, and then to the frequency transmission, means how to represent those sideband or those modulated signal in the frequency spectrum. And one more important thing, for this modulated signal, if it is a multi-tone signal we have identified, and here we have considered that FM2 is greater than FM1. So that means what will be the bandwidth of this multi-tone signal? So bandwidth of multi-tone signal calculation is very easy. From this you can see this is your lower frequency, okay, and this is your higher frequency. Lower frequency component and higher frequency component. So what will be the bandwidth? So bandwidth is equals to higher frequency minus lower frequency of a multi-tone signal. So lower frequency is which one? Fc minus FM2, Fc plus FM2 minus of Fc minus FM2. So if I am solving this, I will get twice of FM2. So that means it indicates what? The bandwidth of a multi-tone signal depends on the maximum frequency present in the multi-tone signal will be multiplied with 2 factors. So here I can write the bandwidth of multi-tone signal is twice of F max. Fmax means the maximum frequency available in FM1 or FM2. If maximum frequency is this FM1, here it will be FM1. If maximum frequency is FM2, here it will be FM2. As we have considered that FM2 is greater than FM1. If FM2 is greater than FM1, that means my bandwidth will be twice of FM2, because out of these two, FM2 is maximum. So my bandwidth is twice FM2. So with the help of this, what happens? The different segments are created, interference is less, and it can be transmitted to a longer distance. So these are the fundamental representation of single tone modulating signal, multi-tone modulating signal, as well as represented in modulation index, either with respect to single tone, either with respect to multi-tone, and what are the bandwidths available in our AM signal. If it is a single tone, what happens, and if it is a multi-tone, what happens. Okay. So these are the certain fundamental things which will be identified further while in demodulation process as well as in modulation process. Now we are going to discuss the signals. What sort of signal? Whether it is a over-modulation, under-modulation or critical modulation. So far we will start with critical modulation. So critical modulation means the amplitude of carrier and amplitude of your modulating signal is same. If it is same, your representation of a modulated wave will look like this. This is your modulated signal. It will just touch at the zero crossing, and your carrier is available here. And in this case, there is no phase change of the carrier, neither the change in the frequency. The frequency remains constant, and this touches means the upper lobe touches with respect to the lower lobe at the zero crossing point. This sort of figure will come out if the modulation index is 1. In this case, you can say the amplitude of modulating signal and amplitude of carrier signal both are same, due to which the critical modulation happens. Okay. Next, if it is over modulation means, in this case, this is the envelope, this is 0, okay. In over modulation, what happens? Your modulating signal amplitude is greater than carrier. If the amplitude of modulating signal is greater than carrier, overlap distortion will be there. Slope overlap distortion will be identified. Now for that case, you can see that the zero crossing, there will be points will be identified like this. The carrier is available at this particular point, but here what happens? Phase change, but frequencies also remain constant, but phase change. If the phase change, that means it will create a noise. So this is called as envelope distortion. This particular part is called as envelope distortion. If anything which distorts the information is called as noise. So this envelope distortion contribute the internal noise in your AM signal, due to which the extraction of original signal will not be same as what I am going to transmit. So for practical case, we are avoiding this particular modulation scheme, because in this case your modulating signal amplitude is greater than the amplitude of your carrier signal. Okay. So for practical case, critical modulation and the under modulation, what we have seen in our frequency spectrum, that we are going to use. This will contribute an noise to your information. Okay. So for today, we'll end up at this particular session, and we'll discuss these all relations and all with respect to others scheme.